So my name is Rusty Towell, and I appreciate everyone coming to Abilene. Thank you very much. This is my hometown, and it's a great honor to have you all come here. I've been coming to several of these conferences and much more exotic locations. I tell people all the time that Abilene, it's a great place to live, but I wouldn't want to visit here, and I appreciate you all for visiting here. So thank you for coming. This partnership we have between ACU, between Natura Resources, is a partnership that's unlike any others, but it's a collaboration that's designed to get things done and move forward. And so we've taken the challenging task of advanced nuclear reactors, we've broken it down into a large series of smaller steps, and we've said how many can we do, what can we tackle in parallel, and how can we tackle it together, a university, a lab, an industry sponsor, and the goal here again is to get things done. We believe this technology will make the world a better place, and we're not interested in doing it in our grandchildren's lifetimes, but we'd like to do it soon. The ACU mission is to educate students for Christian service and leadership throughout the world. So when we're thinking about this technology, we're thinking about doing the research on it, but we're also thinking how can that technology be deployed and make the world a better place. Next Lab, sponsored by Natura Resources. Next Lab stands for Nuclear Energy Experimental Testing, and we're really focused on finding global solutions to the world's critical needs. And if you heard me talk before, you've never heard me talk without it talking about these, and I don't want to waste a lot of time on it, but the why we're doing what we're doing is important, okay? We are trying to do things that matter to the world. The world is full of people, billions of people that do not have a clean, reliable energy source that doesn't put their own health at risk. And so we have about 40% of the world's population that is using animal waste or some sort of biomass as their primary energy source. And when you do that, you burn that in your home for heat or for cooking, you end up breathing in those fumes, your standard of living is very low, and you suffer from it. So if we really want to bring people out of poverty around the world, then what we need to do is provide energy that's clean and affordable and safe. Another critical need, there's one person in this audience that doesn't know somebody that's dear to them that's suffering from cancer right now. Cancer, 1 in 2 of us during our lifetimes will suffer from cancer, and last year 1 in 6 people died of cancer. There's a lot of treatment out there for targeted alpha therapy. We just need to get our hands on these alpha emitters and other types of medical isotopes there's a shortage of around the world, and we can do that with this technology. And then the third thing, talk about water. A third of the world need clean water. We use it for drinking, but in addition to that, a lot of sanitation. If you're talking about agriculture, if you're talking about West Texas, water is always an important thing for us. When I talk about water, you can replace that with high process temperature heat for industry of a variety of sources if you want to think more broadly. This quote from the United Nations says, nuclear energy is indispensable for eliminating poverty, ending hunger, providing clean water, affordable energy. And that's why we think molten salt reactors provide the answers to the critical needs of the world. So the mission of ACU's Next Lab is to provide global solutions to the world's need for energy, water, and medical isotopes by advancing the technology of molten salt reactors while educating future leaders in nuclear science and engineering. We need to develop the technology if it's going to bless the world, but we also need to develop the workforce that's going to enable it to not just stay in one lab, but be deployed across the world. You'll see several of our young students from our labs here with us today, and you'll get to see them tomorrow also if you come to our labs. Nuclear power is currently the safest energy source in the world, but we can make it safer. Nuclear power is currently the cleanest energy source in the world. If you talk about volume of waste produced or how well we are containing it, but we can make it cleaner. It's efficient, we can make it more efficient. Old nuclear did one thing, produced electricity. New advanced nuclear molten salt reactors are multifunctional. They can produce the medical isotopes that doctors need to treat cancer while we're also producing the electricity and providing sources of high process heat to produce pure water. They're scalable. We can build reactors that are small to very large grid size things so that we can make the right size supply for the right needs so we don't have to have the huge distribution lines strung across the country. Carbon-free, obviously, reliable. The state of Texas really took a gut punch 2 years ago when we had a winter storm and when millions of people were without power for most of a week. We had hundreds of people across the state die because our electricity wasn't reliable. So there's a human cost to have an unreliable electricity. Finally, molten salt reactors can use a very wide variety of fuel types, including thorium, and that might be important to this group. What's different about the reactors we're talking about building, or we are building at ACU, and the reactors that are deployed around the world today? The two main things is that first of all, we're using molten salt as a coolant. How many people in here have seen molten salt? In person. You raise the temperature up enough and it turns into a liquid. As soon as salt transitions into a liquid, it's a molten salt. Picture on the right is just a little beaker full of something. It looks like an oil or something else. No, it's a salt. It allows us to operate at very, very high temperatures while simultaneously operating at low pressures. So a high temperature gives us the great thermal efficiency. We're more efficient at converting thermal energy into electricity if we start at higher temperatures. A lot of industry processes require very, very high temperatures, which means you're either burning hydrocarbons, or you're using crazy, crazy amounts of electricity, or you're using nuclear power cooled by molten salt. Why is the low pressure important to us? Well, low pressure means that we don't have to have the huge containment domes, the expense, the cost, the risk, the danger associated with a high pressure system. And it's never, the salts never transition into a vapor, and so you don't have that high pressure, you don't have that danger. And if you use molten salt as your coolant, then you also allows you to have our second key feature, which is to use liquid fuel. Current technology takes solid fuel, takes uranium oxide, puts a metal cladding around the outside of it into long fuel rods. Fission products build up inside the fuel rods over the course of life. When you're questionable about the structural integrity of that fuel rod, you set it aside. And the moment you set it aside, you then call it, in this country, we call it spent nuclear fuel or high-level waste. There's still a huge amount of energy content in there, but we're throwing it into the waste pool. That increases the waste production and decreases our fuel utilization. If instead of using the solid fuel rods, if we take fuel and we dissolve it in the molten salt, just like dissolving your sugar in your coffee so it's spread throughout the coolant, you no longer have a structural solid fuel rod you have to worry about the structural integrity on, and you can use essentially all of the fuel. So fuel utilization goes way up. Simultaneously, you're not throwing it in the waste stream, so your waste production goes way down. And so that's a huge advantage for using liquid fuel. As an added bonus, if your medical isotopes aren't behind that cladding but are free to move through the coolant and be extracted from the coolant, then you have access to those medical isotopes. And we can start thinking about other ways to treat cancer. Obviously, you can't melt down if you start with a liquid, and this is a more efficient way of using thorium. If you want to use thorium in a reactor, putting it in a liquid fuel, the molten salt reactor is the most efficient way of going about that. In 2017, we started a little project. We started a loop that was melting salt. 2018, our molten salt test loop came online, and so for the last 5+ years, we've been circulating salt on campus. In 2018, the Department of Energy heard what we were doing. Ed McGinnis came and looked at it, and he said, this is the future. This is what we need to do. We need to develop this technology. We need to do it faster than China is. We might have missed that boat. They loved the idea of how can we take this technology and bless the world, and they loved what we were doing on campus and educating students, and they said, how are you getting from this small test loop to deployed to the world? Come to DC and tell us about it. Doug Robison, who will speak next, myself, the president of Abilene Christian University, President Schubert, we went to DC and we told the Department of Energy our path forward to go from this little simple test loop to deployed technology around the world is we'd like to build a molten salt research reactor on the university campus. We have the resources to do it, but we need the Department of Energy to provide fuel for us. The flibe salt from Oak Ridge that's been sitting there since the 60s, if you can provide those things to us, then we can move forward with this. And it took them most of 2019, but before the end of the year, they gave us a programmatic letter of support. And that's when this project really took off, this goal to build a reactor. Doug Robison stood up Natura Resources to answer the world's increased demand for reliable energy, medical isotopes, and clean water. Kinds of sounds familiar. But Natura Resources focused on commercially deployable, right? Not how do we take the research product from the lab and how do we deploy it to the world, because again, we don't bless the world by having a really cool reactor on the ASU campus. That's the starting point, but that's not where it ends. The way you really help the world is by making this commercially deployable. And so that was the focus of Natura Resources. Natura Resources stood up what we refer to as the Natura Resources Research Alliance. It's 4 different universities that all have sponsored research agreements with Natura Resources. So Abilene Christian University, but also University of Texas, Texas A&M, and Georgia Institute of Technology. So these are some principal investigators from all 4 institutions. We're building a molten salt research reactor. What does that reactor look like? It looks a lot like the molten salt reactor experiment that was built on the Oak Ridge National Laboratory in the 1960s. So for 4 years, this reactor operated there. You have some pictures of the core, you have pictures of the control room, and it operated very, very successfully there. So it's not a question, does this technology work? Because it was demonstrated 50+ years ago. We're building off of that. As we think about the challenges of licensing this technology, we're doing things as similar to what was done 50 plus years ago as possible. And so we have a lot of shared concepts between the reactor we're building on the ACU campus and the reactor they built at Oak Ridge in the 1960s. The shared concepts is we're going to use the same fuel, uranium tetrafluoride, in the same salt, lithium fluoride, beryllium fluoride, eutectic mixture. They're both loop designs. They use graphite as a moderator. They have a drain tank at the bottom of it that's put all of this radioactive system underneath the ground in a trench. We're going to have a short lifetime. We're not trying to build a reactor to produce electricity for the next 60 or 80 years. We're building a research reactor that will collect data for us for the next handful of years. It's also a low pressure system, so all that is very similar and very, very familiar to the Nuclear Regulatory Commission. Where we're simplifying things is we're saying we don't need to use high enriched uranium. We'll use low enriched uranium. We're not going to build a 10 megawatt or 8 megawatt reactor. We're going to build a 1 megawatt reactor, thermal. We're going to use nuclear qualified stainless steel 316 instead of some of the more exotic Hastelloy N type elements. We're not going to have a freeze plug to keep the salt up in the reactor loop. We're not going to rely on a frozen slug of salt, but we're simply going to use pneumatic pressure to hold it up there. Makes it much faster to release the pressure and drain the tank. We're not going to rely on control rods for safety, and we're not going to have any cooling water anywhere around. So we've simplified things as much as possible. This is a cartoon of what we're building, but I think it shows the concept. The big volume in the center with the vertical stripes, that's our core. It's filled mostly with graphite, but salt comes in the bottom at relatively cool temperatures. The blue, it gets warmed through the fission process in the core. It goes out through the top, through a reactor access vessel, through a pump, through a heat exchanger where it loses its thermal energy. It goes back down to the bottom of the core, and it's a simple loop. Forced flow of flibe salt through the core. At the very bottom of all this is a drain tank. The only thing that keeps the salt up in the loop while you're operating is the pneumatic pressure on the drain tank, and there's a pipe to the left that goes up through a valve that equalizes pressure at the top and bottom. If you want to shut this thing down, you don't scram it, you don't insert control rods, you simply flush it, right? You release the air pressure and allow gravity to do its trick. And so this system is walk-away safe, and everything I just described is inside of what you can think of as a large oven. It's a reactor, so we can't call it that. We refer to it as our reactor thermal management system. But as you go out from if we talk about the layers of safety here, as David mentioned, our first layer of safety is the salt itself. Radioactive material is retained in that salt if there ever was a leak of salt. It doesn't flash to steam and drift around the world, and if it had radioactive material in it, radioactive material would drift around the world, but it falls. If you have a catch pan, it falls into a catch pan, and as it cools off, it becomes a solid. And so if you have any impurities or any radioactive material, it's right there in your solid chunk in the catch pan at the bottom of the tank. Is it a mess? Well, maybe it's a mess, but it's a mess right there you've contained and you control where it's at. You fix the leak, you melt it, you put it back in the system, you're good to go. Very, very different than a water-cooled reactor. So our layers of safety. Salt first, then the primary pumped loop. Then you have the reactor thermal management system. This is a metal catch pan inside of an oven. Outside of that, you have the reactor enclosure, the outer boundaries of this, and then beyond that, you have the reactor cell. So very much as David was talking about, you have layers of safety that cumulatively ensure that if something goes wrong, there's no release of radiation to the environment or the people. It's a low-pressure system. You shut down via a drain. It's passive heat removal, so you don't have to worry about any sort of active cooling even during a shutdown due to decay heat. This is a picture of the reactor enclosure, so some early engineering designs. The reactor enclosure is about 10 feet diameter, 20 feet high. The left-hand column here is a bunch of salt systems. The second column is a bunch of chemistry that's required, and you can tour the radiochemistry labs. The third column is instrumentation, data acquisition, filters, and all this is leading up to the very bottom right, the Molten Salt Research Reactor. We can't build one of these things in this country without the permission of the government. We have to go through this hurdle. Is it the most efficient hurdle? Can it be streamlined? We hope for the future a better licensing process, but what we're doing is we're moving forward right now. And the easiest way to get a reactor license today is to come with a small reactor, a research reactor in particular, and so that's the pathway that Natura Resources and ACU is going. Earlier this year, they invited me to go to D.C. to present to the commissioners about how
advanced research reactors, we're going to help with the deployment of advanced commercial reactors. So they understand our role. They understand not only what we're trying to do, but how we're trying to build this reactor so we can collect the data, we can understand how it works, and so that we can then move forward. We, being Natura, along with the Research Alliance, can build those reactors at a commercial scale and deploy them to benefit the world. We've answered over 300 questions to the Nuclear Regulatory Commission. We have one, you want to count it, left, and we're very close with that, so we're very optimistic. We're about to wrap up the construction permit discussion with them. We have already gotten our environmental assessment report from them last month, and it contains officially a finding of no significant impact. So their words are, it's either so small as it doesn't matter, or it's actually unmeasurable type of impact. We're going to build a small reactor inside of a pre-existing building surrounded by a lot of concrete. There is no safety risk or environmental impact to this. And that was pretty exciting to us because we have just built the building to put this reactor in. Using a never used before regulation from Atomic Energy Access, you can apply to build a reactor in a pre-existing multi-purpose, and in parentheses, i.e. University Research Facility, close parentheses. That's what it says in the regulation. Never been done before, but we employed that.
The construction is expected later this summer, and the picture on the right is Chair Hansen here touring ACU with Abilene Christian University's President Phil Schubert and Doug and I. And this is the report that we got from the NRC about our environmental assessment. So what is that facility? It's what we refer to as the Dillard Science Engineering Research Center. We are still in the process of moving in. You have this large trench where you have a deployment of a research reactor. And so this is our life-size, two-dimensional version of our molten salt research reactor. This reactor can be built off-site, put on a flatbed, brought in here, and then lowered via crane, just like this poster is, down into the research bay, and that's sort of the way we can demonstrate for the first time a small modular reactor being deployed. Dave, I stole this from Idaho, and we're very thankful. This is an exciting slide. We've slightly modified it, I will say. So this is advanced reactor deployment, and this was exciting to us because late last year was the first time our project got added to this slide. So we were excited. For years, Idaho's had this slide of all the different advanced projects. Most of these projects are projects funded by billions of dollars of federal money. They've been on here tracking it. The thing that's happened, the evolution that's happened over the years is things have a tendency to sort of slide to the right. Delays, things happen. We understand that, delays happening. But we did get added. So the circle at the bottom, next Molten Salt Research Reactor by Natura Resources ACU. We're really excited to be added on there. Two things were on there, Dome and Lotus, popping in 25 and 26. Those are actually sort of facilities, Idaho, that will be used to test advanced reactors. They missed the nation's first facility for testing advanced reactors, the CERC. So we added that on there. So the very picture on the left, we added that. So we modified the slide. And then Idaho National Lab updated this slide. And a couple of these things you'll notice are no longer happening in calendar year 25, but sort of moved over to the 26. So the Project Pele and Marvel have sort of slid up to align with where our project is. So we're excited. We're literally on this leading edge of advanced reactors being deployed. We have a path there. The collaboration that we have here between the university, the other research alliance, and all of us being funded by Natura Resources. So let me give you a summary where we are. Natura Resources Research Alliance is leading the way in molten salt reactor development and deployment. ACU is licensing the first advanced university research reactor with the Nuclear Regulatory Commission. It's the first new research reactor in over 30 years. It's the first advanced reactor ever. ACU has completed our Science Engineering Research Center that will house the molten salt research reactor. So we have a licensing underway. We expect a construction permit this summer. We have a facility that we had the grand opening on last fall, and we're working in now, and you'll get to tour tomorrow. And so we're on the path to be the first operating advanced reactor in the nation. But more important and more exciting than just having a cool toy on one university is Natura is now positioned to be one of the first commercial reactor vendors capable of deploying this technology and meeting the world's needs. Very, very thankful for Natura Resources sponsor of us and all the other sponsors that have helped get us to where we are. Natura Resources has a brand new cool website and encourage you to check it out. And that website includes this video that I would like to show you at this time.
You only get to tout the results of a well that you've never drilled once. And you're going to be wrong when you go around telling people this is what we've done if you haven't done it. What we like to point to is what we have performed, what we've actually done.
I think the big thing for those of us at Natura That's what has attracted us to this project, is the mission behind it. How can we take this technology that has a chance to really bring people out of energy poverty and change people's lives, give them pure water, produce medical isotopes that will cure people? How can we invest in that technology while at the same time we're educating students?
Our research focus at Abilene Christian is on those questions that bear into people's lives, that make a difference in how people are able to live through their life journey. And Natura gets that. The whole reason that they exist is to help us take this technology to the world because it matters.
But we've chosen a unique path, and that's enabled us to go from a relative unknown 3-4 years ago to a leader in the field.
So this building is an example of that. We don't have to give you a drawing of a building, projection of a building. We can walk you through the building.
That world-class facility, one of a kind, the first since 1960 to demonstrate this technology, will give us the answers we need for commercial deployment.
The team is broken down on several levels. At the highest level, we have 4 universities: University of Texas, Texas A&M, Georgia Institute of Technology, and Abilene Christian Universities.
A team of experienced leaders who understand energy, who understand nuclear, who brought in partners that have expertise in these areas, is exactly what's necessary to ensure you got the right people.
To have a test bed where we're actually gathering real-time data and performing real-time experiments is going to greatly benefit us moving forward on the commercial design.
Natura's the partner that says, okay, we take what we're learning, we apply it to the real problems of the world, and then we commercialize that and take it to the market.
Look at what we're doing. Look at what we've done as we continue to perform. That's our obligation. We have to continue to perform. As we continue to perform, then we would expect those engagements to increase right alongside the work we're doing.
We're talking about a world where we have essentially unlimited quantities of clean energy. The opportunities are endless for the impact that we can have.
Dr. Rusty Towell and Doug Robison, Advanced Reactor Pioneers, Abilene Christian University, Natura Resources, 2024 Thorium Prize. So thanks, guys.
Dr. John,
Guys, you really are heroes to all of us in here, and we're your hospitality has been second to none. Texas really does things right, and you got a beautiful facility here, and you got a beautiful outlook on why. I always ask that too. I'm like, why would we do this? I don't care about the how, and so I'm going to hand it to you, Doug, and you can talk more about the why, because you're the best.
Thank you, John. John, you can't do this because you already have a challenge coin. Any Natura researchers, you can't do it. Any Natura people, any Next Lab people. What is the fundamental energy that powers every nuclear reactor in the world? Solar. No. Love. Money. Who said money? There you go. Here. Would you, Rusty, would you give that to him? So Natura funds the research at all 4 universities. I worked 40 years, 150 miles down the road in the Permian Basin. My company, EXL Petroleum, revolutionized the oil and gas industry. If you've heard of shale plays or hydraulic fracturing. In fact, this project was funded for 6 years out of recycled oil and gas profits. Already we're recycling here. If we can put as much power on the grid with this technology as what we did in the Permian, that'll be a job well done. Our job is to fund this research. Fundamentally, this reactor performs 3 duties. It is a research reactor. So it's research and education. We have 150 researchers/students on the project at any one time. I guess at this point, cycled maybe close to 1,000 students through that. Secondly, it demonstrates that you can get a license from the NRC. The NRC has never licensed an advanced reactor. There's 2 companies that have filed construction permits, have been docketed by the NRC. That's Natura/ACU and Kairos Power. The third is this reactor provides data to support the commercial reactors. Straight to commercial has been a failure because if you're talking straight to commercial and advanced reactors, the NRC has consistently said the data does not exist to support that. Start with a test reactor or a demonstration reactor. One of our researchers, Rusty from the University of Texas, made the statement that we need 2 weeks of operational data to support the commercial reactors. I'm not sure if that's true yet. I've learned it just because one nuclear physicist says it doesn't mean I want to hear two or three say the same thing. This is what's going to happen this year. We are going to get our construction permit approved, every indication from the NRC that's going to happen. We're going to file the application for operating license. We are going to complete the detailed engineering design that's being done by Zachary Engineering and Zachary Nuclear at the end of this year. That'll be the first detailed engineering design completed on an advanced reactor, period, anywhere in the country. This is a 1 megawatt thermal reactor. That's a limit imposed by the DOE. Natura has already begun 2 years ago the initial design work on the commercial reactor. We have already started early engagement, very early engagement with the NRC on the commercial reactor, currently designed to be a 250 megawatt thermal, 100 megawatt electric reactor, still a small modular reactor, still transported on the back of a semi, still fits all those qualifications. That work has already begun. A lot of what I should talk about, I can't talk about because we're in a non-disclosure agreements, or we're getting into the kind of the inside corporate strategy of Natura. But 2 months ago, we were approached by a group that we are now looking at utilizing this reactor, this design, as a commercial reactor. We had not anticipated that possibility. It would be a much smaller reactor. If that is indeed the case, Natura may see two product lines moving forward: a micro reactor that'll be this design, that already will be approved by the end of this year, as well as our 100 megawatt electric, 250 megawatt thermal. The way we get there is we get there through partnerships, just like ACU. If you look at ACU, you saw the University of Texas, you saw Georgia Tech, you saw Texas A&M. That collaboration, ACU quarterbacked the effort. The quarterback is never the biggest guy on the field. ACU certainly not as big as these other universities, but has led this effort. Natura is doing the same thing. Natura did not exist 4 years ago. I thought I was retiring when I came to Abilene. That lasted about 7 months. We are partnering with, for example, Zachary Nuclear. That's a 100-year-old company, 100 partner companies inside, 22,000 employees. We're partnering with Zachary. We're partnering with Teledyne Brown. We're looking at other strategic partnerships that gives us the ability to take what's being done here, to engineer, to fabricate, to deploy, to operate. And so the same approach is the ultimate success of this project, and success is commercial deployment of reactors that are affordable. That's what sustainable energy means. It's going to be done depending upon the joint ventures and the partnerships we enter into and the capital available. And that's the last key to be unlocked. So I know John wanted to save some time for Q&A. Rusty, I'm guessing you should come back up because somebody might ask me a physics question.
Is it similar to MSRE?
So that actually was what we went to when in the last couple of months, when we had the opportunity arise, can we take this design and deploy it as a smaller reactor? And we can upgrade to 10, 15, maybe more megawatt thermal without affecting the reactor design. It really becomes a function of what is your, the rest of your exchange system looks like and so forth. Yeah.
You claim that this reactor it's SMR. Can you please specify or elaborate on what aspects of this advanced reactors are modularized?
So we're going to, as Dr. Towell mentioned, we're going to demonstrate. Well, I think one of the principal characteristics of a small modular reactor is off-site construction and then transportation and placement into the research reactor bay. So this reactor, it will be constructed off-site and then transported to Abilene on the back of a semi. There's a 40-ton crane in the reactor bay. We'll lower that reactor down into the reactor.
First of all, thanks so much for this work. So inspiring. I've been an SMR fan since maybe 15 years. It's incredible what you guys have accomplished. Deep tech, hard tech, high CapEx deployments, there's this phenomenon called crossing the chasm, going from pilot to commercialization.
Valley of Death, yeah.
Valley of Death. How do you guys envision navigating the Valley of Death?
Data centers, I think, is the greatest example right now. We just filed responded to a request for information that came from Google and Microsoft and Nucor. If you pay attention to the amount of power being used by data centers and where they're going to get the future power has always been a problem. AI has turned that large wave into a tidal wave. And so the data center industry that is loath to use carbon, and quite frankly, they couldn't pull the amount of power off the grid that they would need to pull off the grid. Those three companies need 10 gigawatt of power by 2030 to 2040. That would be 1,000 of our reactors. That's just those companies. And we're under non-disclosure with other hyperscalers that are needing the same. Conventional thinking is that as industries, and it's not just data centers, you look at clean air capture, you look at manufacturing, refining, not to mention baseload power, as they see that they are not going to be able to get the power that they need for the industry, they're going to start swimming upstream. How far upstream do they swim? Do they swim? And this group has already said they would swim upstream to the point of mining. Well, between here and mining is, are they going to become the capital provider for nuclear reactor projects? That's one path forward that is starting to develop. We won't know until it happens. I think what we do know is federal support in and of itself is not enough. The other is that there is a thought that a sovereign, whether it's in the Middle East or wherever the case may be, will step up and say, we have to have this power, we have to have this technology, and we have to move forward. So that's how you cross that chasm of death. If we keep doing what we're supposed to be doing, de-risking, I carried this project for 6 years with our own skin in the game. At some point, you're going to attract those partners, whether it's industrial or institutional, financial, or sovereign, are going to step up and say, we've got to make this happen.
You mentioned the capacity of 1 megawatt thermal. In terms of the electrical generation size, I would assume you're just going to reject heat. You're not going to try to simulate the power generation. How do you envision the power generation to be supercritical? CO2, is it standard? Who's going to do the development? Are you going to do it in your university, or how do you see that being scaled up and designed?
We've thought about it, and it also is very customer specific, right? If they care about the highest efficiency, then supercritical CO2 is the right way to go. If they care about fastest to deployment and fewest hurdles, then you probably go with something that's a little bit more off-the-shelf solution. It depends on the customer. They really want the high process heat. Do they need the electricity? They want a combination of both. Lots of people have been thinking about taking thermal energy and converting it into electricity, and the appropriate way to do that. So certainly at ACU, we haven't been worried about that. For this reactor, you're right. The first research reactor, that thermal energy is rejected the environment. But obviously, commercial cares about how you harness that and what you do with that. So depends on the customer.
I come from the oil and gas industry. So we talk about turning to the right. So Andrew Harmon, who's one of our VPs right over here, showed me a video of oil and gas guy that talked about turning to the right, and he acted like we were turning a valve. Turning to the right means you're drilling. It's also called making whole. It's not like this, it's like this. I'm not a big fan of power purchase agreements. I see lots of announcements about power purchase agreements, and I can't tell if they're worth the paper they're written on. What we prefer to do, and we're doing it now, is entering into feasibility studies. So I don't think I can say who we're doing this with. We're doing 2 feasibility studies, maybe a third. I want to get our customers' engineers across the table from our engineers before we enter into any kind of agreements. And we understand what their needs are, and they understand what our capabilities are. If we're talking to data centers, they need one specific type. They're interested in electrons. If we're talking to refineries, they may need heat along with power. We have a feasibility study on that technology ongoing as we speak. That is going to be very customer specific. For our commercial reactor, which we anticipate deploying our first commercial reactor by 2030, we need site selection next year in the NRC timeline. And so we're working with potential customers who are providing site selection and capabilities, but it's more of an engineering function than it is starting to have attorneys write contracts.
I'm Ralph McBride. I have a question about when you'll develop the non-commercial as well as the commercial. I'm sure you're thinking about this, considering that you're coming from Abilene Christian, how you'll develop this not as a nonprofit, but as a third world solution for energy shortages. Is that happening now? And what's the timing on that?
Yes, it's happening now. So this reactor at ACU is actually Natura's first deployed reactor. It will be deployed by 2026 if everything stays on track. We've already started the preliminary design on the commercial reactor. We would be moving, quite frankly, we'd be moving faster in a commercial reactor. It's just a function of money. If we had more money available, we are not recipients of ARP-20. When ARP-20 was issued, Natura didn't exist. So we've moved very quickly on private investment. My concern about getting to third world countries, and Governor Abbott here in Texas had a directive in August of last year to form the Texas Advanced Nuclear Task Force. I'm serving on that task force. His directive was, how do we get advanced nuclear to Texas? How does Texas become the leader of advanced nuclear? And how do we support the grid with dispatchable power? One of my concerns about data centers is data centers that are willing to pay 3.5 times going rate of power for the grid could snatch up every advanced reactor that's produced for the next 20 years. So it's going to be really interesting to see how we balance high-paying customers. I say we, I'm talking about the whole industry, with other needs that are more fundamental. I don't know that data centers are one of the world's fundamental needs. Maybe they are, but that's going to be the market challenge we're going to have to navigate our way through.
I wanted to thank you for what you're doing. I come from California, and I know this would never, ever happen in California. So it's kind of nice to be in the energy center of America. I wanted to ask about the financing of these. I would love to build them in California, but it's probably never going to happen. I wanted to ask how you guys are financed today and how you envisioning structuring these deals with, in particular, process heat. For example, are you talking to the energy trading companies who want to buy options on commodities? How do you think about structuring these deals in the future?
Currently, everything is financed through private investment, individual investment. We just closed our last financing round Friday. That was oversubscribed, so that's a good thing. I haven't thought about commodity exchanges as being a financial source. It could. As I mentioned earlier, I anticipate, and it's just not me, it's Guggenheim has been speaking for the street for several years on how the capital is going to flow into advanced nuclear. Their tune has changed a little bit over the last year or two, but I think I agree with what they're saying is that either a sovereign is going to do it, so that's a nation somewhere is going to step up and say, we're going to make this happen, or technology companies. Now, a technology company would then, I would argue that the RFI that we just got, the request for information that we submitted our application, and it was Natura and Zachary and others. Can I say, Andrew, are those public who participated in that RFI that we submitted? I'll leave it at Natura, huh? Okay, Natura and Zachary and others that participated in that. That is technology stepping up and saying, we want advanced nuclear. Now, they have not swum upstream to say we're going to fund it, but they have said we're going to issue power purchase agreements that I just said I'm not that big a fan of. The public market has not yet proved itself. We see NuScale in the public market. They've had their ups and downs. Oklo apparently is going to the public market. X-Energy was going to go to the public market. They pulled that back. I don't know if that's going to happen or not. So the public market has not yet proved itself. So I'm a big believer in individual investment and the free market. And I don't think we survive via federal or state funding. I think that's a pathway to nowhere if you're not careful. I'm hoping the industry or capital will step up.
I'm wondering if baseload, is nuclear power forever going to be in that pinhole into that baseload job? Even a data center has diurnal patterns, increased power usage during the day and the night, especially if we're talking about local plants or local commercial, you have these patterns. So do you have any plans to do in your research, like variable power output and how to manage that and how to account for that?
Reactors can do load following, right? I mean, I think the Navy is a great example of decades, of thousands of reactor years worth of variable, load following. So it's possible. Anything would prefer steady output than changing dramatically. So to me, I think the future lies with multifunctional aspect of the reactors, where you produce electricity and high process heat, whether that's to desalinate water or produce synthetic fuels or to produce hydrogen. And so you have multiple outputs, and when you need more electricity, you produce all electricity. When there's not the electrical man, then that's when you produce hydrogen or synthetic fuels or desalinate water or something like that. But that's, again, that would be end user. How do you want to utilize that resource? So I believe there's a bigger future for nuclear than just base load power on the electric grid. Thank you all for your attention. Thank you for coming to Abilene.
There you go. Don't trip with that in your hand.